أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. Today we will be talking about basic postulates of probability. This lecture is a part of lecture series from the course of Statistical Mechanics, having the course code of PHY231. In today's lecture, our basic objective is to understand the isolated systems. We also need to know the equilibrium states and the condition for equilibrium. And at the end of the lecture we will go through the concept of basic postulate of probability. So let's come toward the understanding of isolated system. Normally we consider an isolated system to be a system which has no interaction with the outside world. So this is a type of ideal phenomena in which we consider that it is not exchanging energy or particle with the outside world. So if we look toward it, the laws of mechanics tells us that the total energy of this system is conserved because it is not exchanging the energy with the surrounding and the particles with the surrounding. So that is why the total energy of any particular isolated system is always conserved. So this is one of the basic property of the isolated systems, that its total energy is known to us and it is conserved. If we consider an isolated system, the total energy is constant and the system is characterized by that particular energy. So coming towards these accessible states, all microstates accessible to it must have this energy E, because this energy is constant, is not changing. So for many particles there are usually a huge number of states with the same energy. So a question arises that what would be the probability of finding the system in any one of these accessible states. So the answer of this question comes to us from the basic postulate of probability. So if there are more than one accessible states, so what will be the probability of finding the systems in any of these particular accessible states? So before answering, we also need to understand another phenomena that is very important to us, and that is called as a equilibrium. So equilibrium, as actually we consider a system to be in equilibrium for which the macroscopic parameters characterized to it are independent of time. Or in other words, we can say that when its macroscopic parameters are not changing with time, so this system is considered to be in state of equilibrium. So this is a particular definition or understanding of the equilibrium states when its macroscopic parameters are not changing with time or it is independent of time. So we are combining both the concepts together, the concept of isolated states and the concept of equilibrium. We are assuming a system that is actually in isolated states and that is also in equilibrium. So in the absence of any experimental data on some specific system's property, we can really say about this system is that it must be in one of its accessible states. So if we know this, we can handwave the following, just like there is nothing in the laws of mechanics, classical or quantum, which would lead us to suspect for an example of similarly prepared system that we need to know. And that is why we need to find out all the accessible states. So finding the accessible states, or in other words finding the microstate, is another things we need to know. So it seems that reasonable to assume that the system to be equally likely to be in any of its accessible states. So this is if there are more than one accessible states. So what will be the probability of the system to be in any of its states? So coming toward the postulate of probability, it is considered or it is assumed that the system would be found in any one of its accessible states. So normally in equilibrium case, and when we are treating the system in a statistical mechanics way, we often do some assumption, and for that purpose we need to develop some postulate. And this is the first postulate of probability, the only postulate of probability. And the definition of that postulate is like that is actually the fundamental postulate of probability or even statistical mechanics, that any isolated states in an isolated system in equilibrium is equally likely to be found in any one of its accessible states. The simple understanding of this statement is that if a system has many possibilities, so according to the postulate of probability, the finding of the system or the occurring of this event in any of these particular states should be equally probable, or in other words is like that the probability of finding the system in any of its possible states, accessible states actually mean possible states, in accessible states would be equal to each other. So this is the only postulate of probability, and with the help of this postulate we can solve different problems. So this is also called as a postulate of equal priori probabilities. So this is the basic postulate what we will use throughout in the course of statistical mechanics, and we can solve some problems on that, because there are several steps to solve some problem through statistical mechanics. And in the third step we need to implement the idea of basic postulate, and based on this postulate we can solve the problems of statistical mechanics. So the very important things what we need to understand in statistical mechanics is the basic postulate, and this fundamental postulate is repeated several times, and this is keep in mind for equilibrium configuration. As in the beginning of the lecture we understood that the system should be in equilibrium and it should be isolated. If the system is not isolated, so it will exchange energy with the surrounding. So we don't know the exact magnitude of energy, so we cannot implement or we cannot apply the basic postulate on it, and even we cannot treat the system statistically. This is the first thing, because its energy is continuously changing with time. So that is not isolated whether it is increasing or decreasing, but there is change in the magnitude of energy. The other important condition for implementing or applying these statistical mechanics ideas on any particular system is the equilibrium configuration, that the system which is actually an isolated system should also be in equilibrium. By equilibrium means that its properties are not changing with time, or it is independent of time, is macroscopic property. When its properties are not changing, there is no endothermic or exothermic reaction carrying on inside the systems, so the properties are not changing. I mean, this energy is constant, other properties are constant, is not changing with time, so we consider this system to be in equilibrium. When this system is in equilibrium, we can apply the ideas of classical the quantum statistical mechanics, and then use the basic postulate of probability on that. So any isolated systems in equilibrium is equally likely to be found in any one of its accessible microstates. Microstates are actually all the possible states for any particular system, and this is actually the postulate of equal probability. So with this postulate we can understand the ideas of classical thermodynamics, classical statistical mechanics, and quantum statistical mechanics, and this is actually reasonable to us and does not contradict any laws of classical or quantum mechanics, but it is valid and true. For this purpose we need to remember that physics is an experimental science and it is based on experiment, but along with the experiment we also develop a theoretical justification for that. So this is actually the way to develop a theoretical justification for any particular systems. So the only practical way to see if this hypothesis is valid is to develop a theory, and that should be based on it, and then to remember that. So comparing the prediction of a theory based on it with experimental data, this is something we need to do. So for this, a huge quantity of data taken over 250 years exists. So this is a bit complicated things where we are comparing the theoretical ideas with the experimental values. So for the justification and the understandings of these systems becomes useful to us. We need to solve some of the basic problem based on the basic postulate of probability, and we are considering some isolated systems that are in state of equilibrium, and then we solve some problems on that. So that will be real type problems, and we can have some so this sort of problems in exams as well. So this is a practice of problem for the student to solve some problem and then calculate their probability. So for this purpose we have a simple problem. We have a basic of 3 spin, an isolated system in equilibrium. Suppose that the total energy of this system is considered to be E is equal to minus mu h. So we have seen that only 3 possible system states consist with this energy. What will be the possibility? Just like up, up, down, and up, down, up, and down, up, up. So if we use the fundamental postulate, then the system is in equilibrium and it is equally likely with this any of its possible states. So if we apply this condition, so there are 3 possible states over that, because in this case it will cancel to each other, 2 will cancel to each other, and 1 will be up. This is actually the 3 possible states, and the possibility of the system to be in any of these 3 possible states is equal to each other. So 3 spins isolated and in equilibrium, total energy is equal to minus mu h. So the 3 possible states are depicted here. Is here. Over here, this is the first state, this is the second state, and this is the third state. So if we use the fundamental postulate of probability, what it says that the system is equally likely to be in any one of these 3 states, because there are 3 microstates for these systems. So we can calculate this probability to be 1 over 3. This example I had also given in the physical classes when we had a toss, a coin, or maybe we have some other different shapes objects in which the probability of each phase depends upon the number of phases that body have. If we have a coin that have 2 phases, so its probability of each phase is equal to 1 over 2 or 50%. If we have an object that have 5 or 6 phases or 4 phases, so correspondingly its probability will be 1 over 4, 1 over 5 or 1 over 6. So this is a particular example for that. So if we have a system that have 10 phases or 10 microstates, so correspondingly its probability will be 1 over 10. So this probability is about the systems, not about individual spins, because in this condition it is very clear that it is not equally likely to be in any one of the spin up or spin down state. It is actually in this particular 3 states this system should be found. We have some other examples. We consider particles n, that is around 10 to the power 22 spins. Each spin with each has a spin of 1 over 2, and we need to put the system in an external magnetic field that is H. So the total energy is measured and found to be is equal to minus mu h. So this thing is similar to the 3 spin system, but now there are huge number of accessible states. Is the example just I had given to you for 1 over 10 or 1 over 20 or 1 over 1000. So because the number of accessible states in this case is huge, that is around 10 to the power 24. So what we need to do, the number of accessible states is equal to the number of possible ways for this energy of n spins to add up. So if you want to find out this probability of these systems, what will be its probability? That will be 1 over 10 to the power 24. This will be the probability of each of the particular spins or accessible states. So again, the fundamental postulate of probabilities is the same for this system irrespective of the possible states, whether it is greater or lower. The fundamental postulate is same for all of them. So what it says, when the system is in equilibrium, it is equally likely to be in any one of it this huge number of states. So it says a possibility to be in any one of its possible states, and that is the particular case for it. We have a third example, that is example of classical illustration. And in this example, we need to consider a one-dimensional classical simple harmonic oscillator having the mass m and with the spring constant k, position x, and momentum p. The total energy is equal to 1 over 2 p square divided by m plus 1 over 2 k x square. So E is determined by the initial condition. If the oscillator is isolated, E is conserved. How do we find the number of acceptable states for this oscillator? So what we need to is a phase space. In this space, the energy is constant. So the first thing, the equation 1 is the equation of ellipse. So we need to consider this thing in the upcoming slides. What you need to know, the oscillator energy exactly. The accessible state would be points on the ellipse, and in reality we never know the energy exactly. That is always limitation come from the uncertainty principle, and we say that if you are finding the energy and the position of a particle, there is uncertainty in any of them. So we cannot measure both the things simultaneously. So there should be uncertainty in the energy of that things. Just like if we see this is del E, so there will be it is very less than E. So there should be some uncertainty in the energy of the particles. So for this geometrical picture in the position momentum space, what we have, we need to the energy is somewhere between two ellipses, and one corresponding to E and the other corresponding to E plus del E. So this is something what we get, or what we want to know, that there is some limitation for us to calculate or to measure the energy and position of the particles simultaneously, and this limitation come from the uncertainty principles. So this is the simple illustration of the previous example, where we have drawn these things in the xp plane. X is the momentum and position plane. This is the momentum axis, and this is the position axis, and this is the momentum axis, and this thing is drawn, and this is the space between two ellipses. So the energy is somewhere between the two ellipses, one corresponding to E and the other corresponding to E plus del E. So space cell between two ellipses. So what this is actually the energy, and there is the uncertainty in between this energy. So this is the simple example from the classical statistical mechanics, where we have some limitation to calculate or to measure the properties of these particular systems. So again, if we use the postulate of probability on these particular systems, for this many cells in this phase space area between the ellipse, that is H0, that is very small, a huge number of accessible states are possible for this oscillator with energy between E plus del E. So that is why there are many possible ways for X position and momentum for a set of oscillator in an ensemble of such oscillators. So the fundamental postulate of statistical mechanics is again the same, but it is a bit changed for this particular configuration, and its statement will be like that all possible values for position and momentum with energy between E and E plus del E are equally likely, are equally possible, are equal, their possibility or probability is equal to each other. So this is started with any particular configuration when we have a phase space, that is the space between space of position and momentum, and we want to measure that. So from that we can calculate the most probable behavior of a system as a whole, and we can have some sort of things for that. So again we can use the concept of equal probability of that, and from that we can find out the all accessible states that will be. We have some other example, that is the example of uh, spin up and spin down. And for this we have three particles. Whether what is the possibility, we can see all the possibility of these particles and their solution. We need to consider three unconstrained and distinguishable spin 1/2 particles, and we need to calculate the probability of spin that two are spin up and one is spin down. So if you want to find out the probability of that, that is very easy. This is, we can find out all the possible states, and from that we can find out the probability of occurrence of this particular configuration is p is equal to 3 or true, because in this case we have three configuration where two are spin up and one is spin down. One is this one is this one, and other is this one. So that is why the probability is equal to 3 or 8. This is the time we need to solve the time Schrodinger equation for that to completely specify these systems. So, and we can find out the, if we have large number of particle, again we need to deal with that. So these are some other example for the student when they have time. It is very easy problems, and we can solve when the particle has and the number of particles equal to g, and their spin is equal 1/2. How we can find out this possibility, different possibility when this is another example for external magnetic field, where its energy is equal to mu dot h, and from that we can calculate this probability. The same problem has been repeated for the total energy and the total magnetic field of that systems, and the different arrangement of the systems. So for all these particular states, the energy of this particular system is equally probable, and its possibility is always equal to each other, and this is actually the basic postulate of probability. So thank you very much for listening the lecture.